This chapter is titled Thermochemistry, which is the study of heat involved in chemical and physical changes. We'll learn how energy moves in chemical reactions, how to measure heat flow, and how to apply concepts like enthalpy and calorimetry. These ideas are critical for everything from our metabolism to combustion engines to nutrition labels, even. This shows a picture of what we could call energy in action. It shows a match being struck, and it's an example of a combustion reaction. Combustion releases energy in the form of heat and light, which is the focus of thermochemistry. Every time a chemical reaction occurs, energy is involved. And this image captures that in a real world example. Thermochemistry is about the heat absorbed or released during chemical and physical changes. Some examples would include metabolizing our food, burning gasoline or coal, converting raw materials into other usable products. All of these involve energy transfers that we can measure and predict. And this just shows some examples of energy in our daily life. So this slide A shows a cheeseburger, which provides us with metabolic energy. B shows gasoline, which is combustion to power a car. And C is coal being used in industrial processes like making steel. And these examples show that energy from chemical reactions is essential to modern life. The definition of energy is the capacity to supply heat or to do work. And there are two main types of energy. There's potential energy, and that's stored energy due to its position, composition, or the condition that it is in. And then there's also kinetic energy, which is the energy of motion. Chemistry focuses on how these forms of energy are transformed during reactions. And here we have a picture of a waterfall. That's in picture A here. At the top of the waterfall, the water has very high potential energy. And as it falls, the energy becomes converted into kinetic energy. Now, if that kinetic energy flows through a dam, like in picture B here, then the kinetic energy can be converted into electrical energy. And this is a great example of how we can see that energy changes form, but it is never actually lost. The law of conservation of energy says that energy cannot be created or destroyed. It can only be transformed. During chemical or physical changes, total energy becomes conserved. And this is the foundation of all energy-related calculations in chemistry. And there's a video link here as well. Thermal energy and temperature. Thermal energy is kinetic energy due to the motion of atoms and molecules. Temperature measures how hot or cold something is. And that's related to the average speed of particles. If particles are moving faster, there's a higher temperature, and we would say that that's something that's hot. If they're moving slower, then there's a lower temperature, and we would say that it is cold. Here in this diagram in A, the hot water molecules are moving faster, and the cold water molecules are moving much slower. And this is just an illustration of how temperature can reflect molecular motion. Notice also that the hot particles are a bit farther apart than the cold as well. Thermometers, there's two thermometer types. There's a liquid thermometer, that expands and contracts based on temperature. And then there's something called a bimetallic thermometer. They coil or they uncoil based on how these two metals respond to heat. But ultimately, both of them rely on thermal expansion to measure temperature changes. The definition of heat is the transfer of thermal energy between two different bodies at different temperatures. And we say heat is the letter Q. We denote heat as Q. Heat always flows from a hotter object to a colder one until both objects reach the same temperature. When those two objects end up reaching the same temperature, we call this thermal equilibrium. So here in figure A, we have a hot temperature item and a lower temperature item. And then when these two bodies they come together, the hot and the lower temperature, the hot starts to transfer to the lower temperature, and this reaches a state of equilibrium eventually. So you can think of this as balancing out the heat. It is very difficult to go in the other direction once equilibrium has been achieved. So it's already, once you reach equilibrium, then even if you separate the hot and the cold, they're probably going to stay the same temperature unless another outside force is significantly warmer or colder. Exothermic and endothermic processes. An exothermic process releases heat. And a great example of that is combustion. Combustion can occur when using an oxyacetylene torch. That's an example there. In an endothermic process, it absorbs heat. And a great example of that is these instant cold packs. They're the opposite types of energy change in chemical reactions. And so this just shows us how reactions can either warm or cool their surroundings. Heat units. 1 calorie raises 1 gram of water by 1 degree Celsius, or 1 Kelvin. 1 calorie with an uppercase C is a large calorie, also referred to as a kilocalorie, and that equals 1,000 calories with a lowercase c. When we look at a nutrition facts label, we are looking at kilocalories. So it will tell you if maybe it's a drink that you're drinking has 100 calories, it will say calories and it means kilocalories. So if it says 100 calories, that actually means 100 times 1,000 if we're going to calculate these calories with a lowercase c. The SI unit of heat, work, and energy is the joule, and that's abbreviated with an uppercase J. 1 lowercase c calorie equals 4.184 joules. And 1 joule is the energy that's used when 1 Newton of force moves an object by 1 meter. You will also see joules in physics classes if you are doing other sciences. So it's not just in chemistry, it's how we measure heat scientifically, and it's an SI unit of energy. The joule is named after James Prescott Joule, and he helped define the relationship between energy and work. Heat capacity, also letter C, it's uppercase C, It is the amount of heat needed to change a substance's temperature by 1 degree Celsius. Heat capacity is what's called an extensive property, which means that it depends on the amount of material that's present. Larger objects have higher heat capacities than smaller ones that are made of the same materials. The formula for heat capacity is equal to heat divided by change in temperature. Specific heat capacity. Specific heat is the amount of heat that we need to raise 1 gram of substance by 1 degree Celsius. So very much related to heat capacity. So heat capacity, again, is just the amount of heat that we need to change a substance's temperature by 1 degree. But the specific heat is how much heat we need to raise 1 gram of a substance by 1 degree. Specific heat is an intensive property, so it doesn't depend on how much material you have, because we're just talking about 1 gram of the substance, and it's a unique number for every substance. And the formula is specific heat capacity equals heat divided by mass times change in temperature. And here we have these two frying pans. There's a large and a small cast iron pan. They have the same specific heat. So 1 gram of cast iron is still 1 gram of cast iron. Doesn't matter if it's on the bigger pan or the smaller pan. But they have different total heat capacities because the larger pan has more mass. This table shows us specific heat values for substances like water, iron, copper, gold, and much more. And depending on which textbook that you're looking at, you will be able to find the specific heat of these substances somewhere in your textbook. Most likely, it will be in the back part of your book in the index, or excuse me, in the appendix, probably in the appendix of your book. So if we want to calculate heat, we can rearrange this formula from here and calculate what Q is. We simply multiply by mass and change in temperature. And when we do that, we get Q equals, or heat equals, specific heat times the mass times the temperature change. If a substance gains thermal energy, then its final temperature is going to be greater than its initial. And that makes sense. It's gaining energy, so it's going to be a higher temperature. It's gaining energy. So we're going to also say that Q is positive because heat is positive. If it loses thermal energy, then its final temperature is less than its initial temperature, and the value of Q becomes negative. All right, here is an example. So when we heat 800 grams of water from 21 degrees Celsius to 85 degrees Celsius, and this 8.0 times 10 to the 2, that's just 800. We just move this decimal place over 2 spaces. First, we want to find the specific heat of water. So you'll probably have to look that up in your book. And it equals, again, it was on the last slide there, it equals 4.184 joules per gram degree Celsius. And that's little c. And this is our starting temperature, 21 degrees. So that's going to be our initial temperature. This is our ending temperature, so this is going to be our final temperature. So we're going to use this equation for heat is specific heat times the mass of, which is how much water there is in this case, and the final minus the initial. So the final temperature is 85 and the initial is 21. So everything that we do with these variables, you can think of as putting it in parentheses, just in case, especially for the temperature part. So if we add or subtract, we have to put that in parentheses in order to do the order of operations correctly. So our final minus our initial 64 degrees, and our mass doesn't change. It's the same. So is our specific heat. And we get a final answer of 2.1 times 10 to the 2 kilojoules. We can rewrite that as 210 kilojoules as well. So what this means is that 210 kilojoules of energy becomes absorbed by the water. This is a picture of a solar thermal plant. Um, Here, they have these mirrors that focus sunlight to produce steam. The steam turns a turbine, and the process ends up converting heat energy into electricity. So these are the mirrors to concentrate that light, and then the heat is transferred here, and then it goes through the turbine, and it creates electricity. And let me see here. This is a solar thermal plant, and it has 170,000 mirrors to concentrate sunlight on these water towers. So it's a little bit different, but they're basically harnessing the energy of the sun, reflecting it back, and it's going on to these water towers here. All right, and here is the practice questions associated with this section.